Okay. The ceiling function looks like this. Basically rounds up your number. And we want to show that no limit exists, so jump discontinuity here. So if the limit exists for all epsilon greater than 0 to 6 at delta greater than 0, such that if absolute of x is less than delta, then fx minus L's absolute value is less than epsilon. We will show there does not exist a delta less than 1. And if it fails for delta less than 1, it must also fail for other values of delta. Because if you show that it doesn't work when delta is less than 1, because you can't be arbitrarily close to the limit, then it doesn't matter if it's not like, oh well, then it would work if delta is less than 2, because delta less than 1 is a subset of delta less than 2. So we can just show that we can't find a delta less than 1. Let's have a look at. So we'll have f of x minus L less than epsilon. Now, we also know that x is less than delta, like we said. So what that means is we have x can be between, and delta some number less than 1. So x can be between minus delta and 0, or x between 0 and delta. If that's the case, if it's somewhere here, then what we'll get is 0 minus L less than epsilon, or, and here, we'd get 1 minus L less than epsilon. Okay, so here we get absolute value of L less than epsilon, or 1 minus L less than epsilon. If we choose, if epsilon was equal to if it were the case, epsilon was equal to whatever you were claiming the limit was, then we are forbidden from having x be negative. And likewise here, 1 minus L, that would be, you'll be forbidden from having x as positive. So we want to go with the minimum of the two, I think. The minimum of L, or 1 minus L. But I didn't really say this last time I did a proof like this, but if L is 0 or 1, then make epsilon, let's see, so if L was 0 or 1, then you'd have minimum 0, 1. So then just make epsilon equal to 1 then. So under this situation, you cannot be within epsilon of L by being inside your x less than delta interval. So yeah, it's similar. to the proof we did last time, I think. Okay, let's have a look at the next one now. Hopefully that's okay. All right, 202. Prove that this one doesn't exist. Okay, so for all epsilon greater than 0, there exists a delta greater than 0 such that if x minus 0 is less than delta, then that means f of x minus L should be less than epsilon. Okay, so again, we'll show there does not exist delta. Okay, we have fx minus L less than epsilon. So either x is rational or x is not rational. If it's rational, you'll have 1 minus L less than epsilon. Or if it's irrational, we'll have 0 minus L less than epsilon. So that's 1 minus L less than epsilon, or L less than epsilon. So choose epsilon to be the minimum of 1 minus L, as long as L does not equal 0 or 1. Otherwise, epsilon, choose it to be 1. So then what will happen is fx minus L less than epsilon will not be true for all x less than delta, for any delta. Yeah. So like, suppose you're claiming that the limit is a half. Well, if you choose epsilon equal to a half, like I should actually write out an example. So suppose someone claimed that the L was equal to a half, then you just choose epsilon equal to a half. So then when you have f of x minus L less than epsilon, this should be true for all x within the interval of delta. So you want to choose an x in x less than delta. Now we don't know what delta is, but no matter what delta is, you could choose an x which is, for example, rational. So then this would become, because it's rational, 1 minus a half less than a half. So you get a half less than a half. So it fails. You cannot be within a half of the limit, for example. Yeah, we could, could try another value. Like, for example, if someone was claiming that the limit is 0, then you will just choose epsilon as 1. So the limit here is 0, and this here is 1, and you get exactly the same problem. 1 less than or equal to 1. Because although we don't know what the delta is, but it's not important, because as long as it's not 0, we'll have an interval where we could choose a rational element for x. So yeah, I think that's kind of what they're getting at with the hint here, what I'm kind of outlining here in this little explanation. Okay, so hopefully that's clear. Let's see now. We got time. We do. What's the next one? 203. Using precise definitions to determine. Yeah, okay, so this one I think does. This one's kind of interesting because I think this one does have a limit. Okay. Right, using precise definitions of limit determine that. So I'm going to claim the limit is 0. So that means for all epsilon greater than 0, there exists a delta greater than 0 such that if x minus 0 is less than delta, then fx minus 0, the limit, is less than epsilon. And I can actually see what the epsilon, what the delta is already. So if you just, it's kind of obvious nearly that delta would be epsilon divided by 2. And in fact, actually, I think the delta would be epsilon would do. Okay, so proof. Okay, so we have f of x less than epsilon, but absolute of x is less than delta, which is epsilon. So then that would mean that either fx is x or 0. If it's 0, we are done, since obviously the absolute is 0 is less than epsilon. But if x, then let's see. So now we have the absolute of x is less than epsilon. But this is true. Yeah. Maybe I shouldn't have said but here. Rather, I should have said also. Okay. Yeah, also that due to the delta being epsilon. Yeah, okay. Okay, that's okay. Right. Using the function from the previous exercise, use the precise definitions to show that does not exist for non-zero a. Yeah, okay. Okay, so this one now is kind of the opposite. Oops. Okay. Right, does not exist. Okay, so for all epsilon greater than 0, there exists a delta greater than 0 such that if x minus a is less than delta, then that should mean f of x minus L is less than epsilon. So I'm going to show there does not exist a delta when epsilon equals what will I choose? Thinking like L over 2 maybe. I think that would do it. Okay, so if you have f of x minus L should be less than epsilon, then what you'll have here is either f of x minus L is, or I should say, x minus L is less than L over 2, or 0 minus L is less than L over 2. Now, x minus A is less than delta. So regardless, we can choose an x in the interval which is, now which one's the one that gives us the 0? Irrational. i.e. x is not q, but x is in the set x minus a less than delta. So then that means we have the case 2, if we want to call this like 1 or 2. So that's L less than L over 2. So yeah, if you choose this as epsilon, then we can show that we can't get arbitrarily close to the limit. Should we consider case when L is 0? What about the situation L was 0? Or could the L be the 0? That might be a special situation, just to show that it doesn't work if it's 0. If someone was claiming that the L was 0, then you would have f of x less than epsilon and x minus a less than delta. So this could be 0 or x. So again, we'll just look at x not being in Q. Is that the one that gives us the irrational? Or no, maybe this time I want it to be rational. X in Q. So you would have absolute of x less than epsilon. But actually, oh, but you have x minus a less than delta. So what was happening here? Yeah, what's happening here, you'd have to be within epsilon of 0, and this one here you'd have to be within delta of a. So this would only work in the case when a would equal 0. Then you could have these two intervals coinciding. So you could have this true and this true only when a is 0, but you're not allowed that. So yeah, okay. I think that proof is okay. Okay, and I think we could leave those 3 for next time because they're like a different category. We want to show that the sum here is, yeah, the multiplication rule, yeah. Sorry, the coefficient being pulled out and multiplication here. Okay, that one looks a little tricky. I'll have to think about, maybe I'll have to think about these. They're not as super obvious about how to do them, but all right, well, that's good. Only 3 left to do. And then we have chapter 2 finished. So one more video should do it. Okay. Thanks for watching. Any problems or mistakes, please let me know. And I'll see you all next time.